Can you guys hear me clearly? I hope you guys are done with the quiz.
Yes, sir.
Okay, so I have shared my screen. So, okay, yeah, let me go to the.
अस्सलाम वालेकुम सर।
Walaikum assalam.
सर ये गैलार्ड की बुक जो आपने असाइनमेंट नंबर 2 भेजी है सर, ये काइंडली सेंड कर दें।
गेलाट की बुक सेंड कर दूं कि आपको ये पे प्रॉब्लम सेंड कर दूं?
सर गैलार्ड की बुक सेंड कर दें।
चलें, I will check that if I have a soft copy of that book. So I will share it in the classroom. Otherwise, you guys should also strive to find the book as well, because in the library you have a lot of copies of this book that they are available in the library. But I will see that if I have the soft copy, I will share it in the classroom. Okay? समझ आ गई कि उर्दू में बताऊं? Okay, I will try to share it. Okay, but first I have to find the book.
ओके
Okay.
सर।
Okay, thank you very much. So as you remember, in the last class we were discussing the compression members. Okay, so we discussed the critical stresses. Okay, and let me remind you that we concluded our lecture that we can estimate the critical stresses in the compression member using Euler formulation. Okay, and if I remember, like if we had this we like this, we have this type of formulation of the critical stresses. I hope that I have not missed out any super subscript or subscript, but I this is the Euler formulation, and with the help of the Euler formulation we discussed that we can estimate the critical load or critical stresses in the compression member. Okay, so what we have discussed so far is that we have discussed that how to analyze or design a isolated compression member. Okay, like we have also have cases that the members which we used as a compression member or as a column, it is braced in the bracing condition about the axis. Like this is an example of a compression member over here. The load is applied and we have two axes. One axis we call the major axis. Okay, this is a wide flange section. Okay, or H section. This is the major axis and this is the minor axis. Okay, the major axis, like when we have the bending about the major axis. Okay, so okay, when we have bending along the major axis, this member will deflect like this. Okay, but when we have bending along the minor axis, which is the y-axis in this case, the bending will be like this. Okay, because the bracing in the y direction or about the y direction, the bracing system is different. This member is being braced at the middle. Okay, over here along the y-axis, you can see along the x-axis or about the x-axis deflection, we do not have any bending or any bracing that is provided to this member. Okay, so in this case you will have different effective length. Okay, effective length in this case will be different. Okay, effective length, and let me remind you what we call effective length. Effective length, we term this, we call effective length k into the length of the member. Okay, where k is support condition. Okay, so it introduces the support condition influence into this length factor. Okay, so if you see that along the x-axis, in this case along the x-axis the KL value will be different, and along the y-axis the KL value will be different as well. Okay, so along the x-axis or about the x-axis, or you can say about x or major axis, the KL value will be about 26 feet. Okay, sorry, 24 feet. And along the y-axis the KL value will be 12 feet. Okay, and these KL values are valid if your support conditions are pinned. Pinned means that, like, if we have this type of situation, like pin, okay, pin. So for pin type of condition, the K value is 1, okay. And if we have this type of situation, which is being demonstrated through this figure, so which is this one, fix. If we have this type of support conditions, the K value, or for this type of compression member with this type of support condition, K value will be 0.5. Okay, so you can see that about the x-axis buckling or about the x-axis buckling bending, the length KL value is 12, but actually the total length is 24 feet. But if you multiply, this is actually KL, and K value is, in this case, is 0.5. This is the K value. If you multiply 0.5 with 24 feet, so you will get 12 feet, okay. Similarly, over here, the support conditions are fixed, okay. We know that this length is about 12 feet, okay, and this is about y-axis. So this will be, the K value is 0.5. If you multiply 0.5 with 12, so you will get this 8.4 feet, okay. So the point of showing this slide is that we might have this situation in the structure that a member is braced in one direction and a member is not, like we can have this type of situation, okay. Like the member, we know that once, as I told you that, okay, let me go into the detail. We have a wide flange section, okay, like this, and load is applied somewhere here. There are two type of axes, x-axis and y-axis, okay. So the x-axis is the major axis and the y-axis is the minor axis, okay. So which axis we call major axis? The axis which has the maximum moment of inertia, okay. The moment of inertia along x-axis, if you compete about moment of inertia about x-axis, so this value will be greater than moment of inertia that you calculate about the y-axis. So the y-axis we call the minor axis, okay. So the member is braced about y-axis because it is susceptible to bending in the y-axis. So that's why you can see in this figure, the member is, bracing is provided for the member if it tries to deflect in the about the y-axis. Is that clear to all of you? Are you getting what I'm trying to explain? समझ आ रही है?
Yes, sir.
Okay, we will go to the next slide, and it is loading now. Oh God. So we have discussed so far is that support conditions, if you have this type of support conditions, fix, okay. So the K value will be, I think, 0.5, and KL we call effective length, okay. This is effective length. And if we have pin support conditions, so we will have, yes, if we have pin support condition, the K value will be 1, okay. So but this situation cannot be reached in the field, okay. It is very difficult to produce fixed support conditions in the field. Whatever type of bracing or restraints we provide at our support, so we can more accurately, we can model it with the pin condition, okay. So in the field, we can achieve pin condition. Dish. Okay. So if we go to this slide, so it is like this fact has been explained on this slide. Like this is an example of fixed support. Okay, fixed support, and this is an example of hinge support. Okay, what it is saying that it is difficult to achieve the fixed or the rigid condition in the field. Okay, and although it is possible that we can achieve this type of provision so that we can model our member with fixed support, but ordinary connection will usually be closely approximated with the hinge or the pin condition. Okay, so although fixed conditions can be achieved with, they can be achieved with the special provisions. Okay, and these example of those special provision has been explained in this figure. Okay, you have to provide a lot of bracing, you have to provide a lot of restraining arrangement at the connection. Okay, but if you have this type of situation, so it can be modified, it can be modeled as a pin. Okay, so this I have already explained in my previous slide that we go for this one. Okay, but for the academic point of view, you will see some of the examples of the problems with this type of support conditions and this type of support condition. And you will also have, you can have this type of support condition that one of the end of the member is pinned and the other is fixed. And if I remember, so this will be the deflected shape here, and the K value for this type of situation or this type of scenario for the compression member is 0.7, if I remember correctly. Okay. Okay, now as I told you that a member can be braced. Okay, a member is braced uh, along the weaker axis. Okay, or along the minor axis. Okay, because we know that we have a load. Okay, we have a wide flange section. Okay, this section. Now we know that where is the major axis and where is the minor axis, but by looking at the geometry of the cross section, so we can place this member with this orientation. Okay, the load is acting at the centroid, for example. Okay, there is, for the time being, we are assuming that there is no eccentricity. Okay, but we can also orient, or we can also place this cross section with this orientation as well. Okay, if we place, this is now your minor axis. Okay, and this is your still major axis. Okay, so in this scenario, let me draw the axis here. Okay, this is your minor axis and this is your major axis. Okay, so we know that the moment of inertia along the major axis is more, or it is higher as compared to the moment of inertia along this axis. So we will orient our member in this position. If we orient our member in this position, so it will be more susceptible to bending, or it is more susceptible to deflection. Okay, in other words, you can say that the deflection will occur in this member at a lower load, when the axial load is not that high, it's lower. Okay, and if we orient our member cross section in this position, so the capacity of the member will be more. Okay, the critical stresses will be higher. Okay, so we can say that the critical load will be higher, and in this position, if we orient our cross section, the critical load will be lower. Okay, it is more susceptible to deflection. If we place our member along the minor axis, okay, it can bend, okay, more easily than it can bend in this scenario. Okay, so when we look at the figure 4.10 in this example, so it is saying that, so it has been braced along the minor axis. Okay, and it is understandable because along the minor axis, if we are using a wide flange section, it is more susceptible to buckling. Okay, along the major axis, the bracing is not provided. Okay, which is the major axis? This is the major axis. Which is the minor axis? This is the minor axis. Okay, this is the minor axis. Along the minor axis, there has been some bracing that has been provided to this compression member, and this bracing is provided at two different at the middle of the member. Okay. Now we have to assume the support condition, and we have discussed that mostly we can achieve more easily this support condition. Okay. So for this support condition, we know K is 1. Okay. And the L is also 13 feet. And if we want to calculate the KL value, effective length, this will be 13 feet. Okay. Okay. So we can see that, or we can visualize from this figure that this member can bend like this due to this bracing. Okay. And the effective length in the along the minor axis is about 13 feet. And in the major axis, there is no bracing provided at the middle of the member. The effective length will be 26 feet, provided the support condition we assume as pin condition. Okay, the K value will be 1. So now you have two effective length values. Okay, now which value you have to use to calculate the slenderness ratio? If you remember that in order to design the compression member, we use two design aids. Okay, one aid was from table 4.1 to 420, I guess, and we call that column load tables. Okay, and we also used another design aid from the manual, that was table 422. In order to use table 422, we have to enter the table with this value. Okay, and in order to use this design aid, we have to use this value, only effective length, without radius of gyration in the numerator. Okay, so we have two effective lengths. Okay, so they have been given. Okay, now what you have to do that in order to demonstrate, or in order to deal with this type of problem. So there is an example in this lecture. That example you can find in the Segway book. Okay, and there is a white flint section. Okay, let me correct you, let me remind you that if we have a symmetrical section, okay, like we have a square, so in this case there will be no major or minor axis. Okay, both the axes have the same moment of inertia. Okay, so none of the direction is susceptible to bending. Okay, like both have the same capacity. Okay, but if you use a rectangular section, so rectangular section, there is a difference. There will be a one axis we will calling at major axis, and the other axis we will be calling as a minor axis. So then you have to take care that you have to orient your member in such a way that its capacity is not so susceptible in the bending. Okay, now there is a white flint section. You can go to the manual and you can check chapter number 1 for its property, and it is 24 feet long, and the support conditions are pinned at both ends. And this member, this compression member, or this white flint section member, is braced in the weak direction. And when we talk about the white flint section, so we should remember that white geometry, or the shape of the white flint section, is like this. So this is the major axis, and it is saying that this member has been braced in the weak direction. Weak direction means this direction, y-axis. It has been braced. Along the x-axis, it is not being braced. Okay, now we have to calculate the slenderness ratio for these two values. Okay, now as I told you that in order to find the properties of this section, you have to go to the manual, and from the manual you will see that the Rx value along the x-axis, or the major axis, is more, and along the y-axis, or the minor axis, this value is less. So you have to calculate this slenderness ratio. Okay, and this slenderness ratio you have to compute for the both in x-axis and both in y-axis. Okay, on x-axis we do not have bracing, in y-axis we have bracing, so we have to use a reduced length. Okay, so this reduced length, that it has been braced at two different points. The length is 8 feet, so KL value will be, K is 1 and L is 8. Okay, in this case K is 1 and the length is 24. Okay, so these two values you have to use, and then out of these two cylinderness ratio, whichever is maximum, you have to use that value. Okay, now in this case, this cylinderness ratio is controlling. Then as I told you, you can use the design aids. Okay, this is table 422. You have to enter the table with this value. Okay, but I told you that in the last class that you have to do the interpolation, because we cannot find for these values for the friction. Okay, maybe the KL, the values are given for 54, and you have to, and for 55 you have to interpolate between these two values. Okay, so if you enter the table and you will find these critical stresses, so if you get the critical stresses, you can multiply it with the cross-sectional area, and this cross-sectional area you can come, or you can obtain from chapter number 1. Okay, chapter number 1, there are some tables. Okay, and we already have a quiz on this table as well. Okay, now this cross-sectional area is coming from the chapter number 1, so you can find the design strength. Okay, so now this was, as I told you, that design strength we have computed using the LRFT approach, and for ASD approach we can still use those tables, and for that table you can enter that table and you can get this critical stress divided by factor of safety, and if you multiply this critical stress with the gross area, so you will get the design capacity. Okay, or the allowable, this is based on the ASD, and 616 is based on the, okay, it is loaded. Why it is loading? Give me a moment. Yes. Oh, okay, so this is 616, and this is 410. Okay, any questions? Any question? आप लोगों को समझ आ रही है?
Yes, sir. So far, so good.
Okay, now, so what we have discussed so far is that we have discussed the analysis, okay, and design of isolated columns. Okay, like this. So in the first case, we discussed isolated columns without or with no bracings. Okay, we can do that. The second case, we have just demonstrated through the example that isolated column with bracing. Okay, so now you guys can deal with the isolated, or you guys can deal with the design and analysis of isolated column with bracing and without bracing. Okay, but we know that you cannot find column as isolated. Maybe in the laboratory you are doing testing on a single column, so you can use these approaches, but actually columns are part of frames. Okay, like you will most of the time when you are designing a building, let's take an example of frame. So this is not isolated, it is connected with this beam. Now how we can deal with the analysis and design of this type of column? So the approach is different. Okay, now let me remind you that what we have discussed so far is applicable to the elastic design, elastic columns. Okay, elastic design, you can say. Okay, so if you have this type of situation, then how we can do the analysis and the design of the columns? So for this type of scenario, we use nomographs, very simple nomographs. There are two type of nomographs. Okay, One developed for frames with sway permitted. The second is frames, okay, with sway not permitted. Okay, but in order to use these nomographs, you need these values, GA and GB values. Okay, for example, this is a column, this is A, and this is B. So we have to compute GA and GB values. And what is GA and what is GB values? So G values is the summation of stiffnesses of beams, I guess, or columns. Yes, columns. I have to see. Okay, so you have to sum up the stiffnesses of all the columns which are meeting at this point, and then you have to divide it by summation of stiffnesses of all the beams which are meeting at this point. So I have to see that this is beams and this is, I think, columns. So you have to calculate this value, stiffnesses of all the members at this point and at this point. Now we have a special case here. Okay, at this point we do not have any beams. Okay, this is a support condition, and if we have a support condition like this and it is a part of frame, so we assume G value for this 10. Okay, and if we have this type of situation, so we use G value 1. Okay, straight away. Now we already discussed that for this point, or for this point, when it is connected to beam, so you have to sum up the stiffnesses. Okay, moment of inertia divided by the length of the member. Okay, this is, I think, beams. Pardon me if I get wrong. I cannot remember. I have to go to the slide and I have to see it somewhere here. Yeah, this one. Okay, this is column is 171 by 12. Joint A is column. Yes, 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 yes. So this is columns and this is beam. Okay, now how does a nomograph look like? So I will go to this slide. So once this is a nomograph. Okay, so there are two type of nomographs. One is for the frames in which the side sways are prevented, like the brace frames. Okay, and the one in which the side sways are not prevented, we call it unbraced frame. So there are 3 columns in these nomographs. So once you calculate the stiffnesses or summation of stiffnesses at a point and you compute it at the second point, you would have to join them together and you will get the K value. Okay, is it clear? Is it clear?
Yes, sir.
Okay, now remember this, like this is A, this is B. So you have to compute GA, GB. Okay, and using these GA and GB values, you will calculate K. Okay, K is unknown and you get it from nomograph. Okay, and remember this approach is valid for elastic design. Elastic design of columns. Okay. For inelastic design, okay, for inelastic design, you have to use a reduction factor. Okay. And that reduction factor is star. Okay. And once you have this elastic value, GA and GB values, you have to multiply it with this factor. Okay. Like this is elastic. Let me write it here. This is elastic. This is, oh sorry, this is B. I have to write this is elastic. So if we want to use we want to calculate the K value for an inelastic column, so then you have to use K inelastic. K inelastic is G elastic multiplied by tau alpha. This factor you can calculate, okay, or you can use a table in the manual, and that table is table 421, and analytically you can calculate this tau alpha, sorry, from the ratio of critical stresses. This is inelastic critical stress by critical stress elastic. Okay. Then you can use the same nomographs. Okay. So it is demonstrated here. Okay. Like how we can calculate the effective length of inelastic columns. So as I told you that this value is like this, how we can calculate the inelastic G values. Okay. Alignment charts means nomographs. Nomographs. Okay. So you have to use stiffness reduction factor, and this stiffness reduction factor is this one. And as I told you that we can use table 421 in AISC. And if I remember with the experience with my previous class, that you can find it from page, it is given at 317, 317. Okay. Now this tau value is equal to ratio of critical inelastic and elastic critical stresses. And actually it comes out to be a ratio between the tangent modulus by the elastic Young's modulus. Okay. You can calculate it once you have these critical stresses, or you know the tangent and you know the elastic modulus of your member. In this is coming from the nonlinear range. Okay. Like if you remember, when it becomes nonlinear, it keeps on changing. Okay. This is tangent modulus, and in the proportion, within the proportional limit, we have this elastic modulus. Okay. Now how we can proceed and how we can calculate this inelastic reduction. Okay. What we call this summation of stiffnesses. Okay, for the inelastic columns. So first you have to calculate, or first you have to estimate these stresses. And if you are using LRFD, so you can directly estimate this. Okay, critical stress. And this, if I'm not wrong, this is inelastic critical stress. PU divided by this factor. Okay. Once you have this value, then you can estimate, you can use this equation. Okay. And you can use this equation to calculate the FE value. Once we have the FE value, we can calculate the critical stresses elastic by multiplying with it with this factor. Okay. But once you have this and this, you can simply take a ratio of these two stresses to get the star value, okay? Okay, now these steps have been also explained on this slide. Like first you have to estimate this inelastic critical stresses with very simple formulation. PU you have to calculate 1.2 into dead and 1.6 into live if you only have dead and live loads, okay? Then you have to obtain Fe value as I told you from this expression, okay? Then you can calculate this critical elastic stresses, then you take the ratio. Once you know this one, you calculate this, you multiply this stiffness reduction factor with the value you have computed, okay? Are you following me? आप लोगों को समझ आ रही है?
Yes, sir.
Am I connected?
Yes, sir.
Yes, sir.
So okay, now this is an example of that table, okay? Like the ta value, ta alpha or t ta a, we have to see, but I would suggest that we will stick with the uh, AISC. Now this is ta a, okay? Now how do we use this table? Okay, we should know the load by the gross area ratio. We have to enter the table. Then for the corresponding material we are using, we just have to pick the value, okay? But we have to enter with this ratio, okay? Like this is given here, okay? Now there is an example that we have to compute this star A value for the compressive stress. Now this is compressive stress. This value is given for this example. It is 25 KSI. No, we know that the ta A is equal to this formulation, okay? Now you have to calculate the inelastic critical stress and you have to calculate the elastic critical stress. And as discussed that how we can calculate the inelastic critical stress with this simple formulation. Okay, pi c value is 0.9. So once you know the critical inelastic stresses, so you have to plug in those values and you have to use this equation, and you have to estimate this value. And using this value, once you know this value, you just multiply it with the coefficient or reduction factor proposed by AISC. Okay, so you will get this value. Once you know this elastic and inelastic critical stress, so you just take the ratio of these two and you will get this star value, okay? Or you can get this value from the table as well, but you can compute it analytically as well, okay? So now we have to use these inelastic or elastic uh, formulation to calculate the effective value, K factor for a column, which is a part of this spread. And there is a column which is column A to column B, okay? Now we have to compute GA and GB value, okay? So, but we have to compute it for the elastic case first, and then we have to multiply it with the ta, okay? Now for the joint A is here. So we have to come up with the stiffnesses ratio. You have, this is a section. For this section, you can compute the I value from chapter number 1, which is 171. Okay, I think this is feet, cubic feet. Sorry, and the length is 12 feet. You divide it by this, so this is I by L. Now at this point there are two beams. So the length of these beams are different. One is 20, the second is 18. So this is the I value, okay? You can take it from the manual. You compute this GA. Now similarly, you can calculate GB. At GB, you have two columns. And they have the same section. So that's why they have doubled the value, stiffness value computed for the single column. Okay.
Excuse me, sir.
Then you have two beams here. This one and this one.
Excuse me, sir.
Yes, please.
सर ये इनर्शिया की आई वैल्यू जो है सर ये हम टेबल से लेंगे
और यहाँ इस स्टेटमेंट को देखें, स्ट्रॉन्ग एक्सिस. What is
अच्छा
the
सर एक्स
strong
एक्सिस
axis? Though once you go to the manual, you will always have two values.
यस सर एक्स वाई एक्सिस
टेबल में मैनुअल में इस तरह होगा, but you have to see which one is y axis. So
ओके सर
yes, ये मैं भी पूछने वाला था. This is y in the table and this is z, I guess. So this value, because it is saying it is lateral load is supported by point, so I am also tired now. Okay, so you calculate GA and GB value. The next step is you calculate this ta A value or ta alpha value. Okay, now we have to see that what is the K value. Okay, now from the alignment chart and the frame is unbraced. Okay, the K value is about 1.45 based on elastic behavior. Okay, now forget about this statement. First you have to check that my column is behaving in the elastic range or inelastic range. And if you remember from the plot of critical stress against the slenderness ratio, like this, and the division between the elastic and inelastic is by this equation. Okay, this is elastic. This is KL by R. If KL by R and this value if is about 113 for this case, if the KL by R value is greater than 1 by 13, it means your column is elastic, and this approach is okay. You do not have to calculate the star values. Okay. But if the values are less than 1 by 13, so then the column is in the inelastic range. This is inelastic. Okay. So this K by R value is 50, which is less than this one. So our column is behaving in the inelastic range, or the expected behavior of this column is inelastic. So what you are going to do is that you want to compute this stiffness, this value, ta value. Okay, this ta value you can determine from table 4.21, or you can use the equations, these equations in elastic. Okay, you can go to the table as I told you, you enter with this value, and this will directly give you ta value. And of course, you need interpolation. Okay, then you have to multiply it with the GA and the GB value with this stiffness reduction factor. Okay, once you do that and you go to the same table, same nomograph, just give me a moment. It is loading this nomograph. Which nomograph? This nomograph. This. Where is my pen? This one. These are the nomographs. Okay, for students like me, which जो जल्दी भूल जाते हैं उनके लिए मैं यहाँ लिख देता हूँ nomographs. You have to use these values. Okay, GA value, GB value, you connect them it will intercept the K value column. Okay, so the K value, you will get it. Okay, so with this, the column or the compression member section is over. Any questions? Do you have any question regarding the what we have discussed so far?
Excuse me, sir.
Yes, please.
सर ये हम जो कॉलम या टेंशन मेंबर सर हम डिज़ाइन करते हैं जो हमने मतलब लेक्चर 5 में और 4 में सर ये पढ़ा है सर तो ये तो सर हम एक एक मतलब मेंबर लेते हैं सर लेकिन प्रैक्टिकल लाइफ में तो सर बहुत से मेंबर होते हैं तो सर हम सब मेंबर्स के लिए डिज़ाइनिंग करनी होती है इस तरह
सब मेंबर देखें आप अगर इफ यू रिमेंबर योर डिजाइन what is the essence of tension or compression member? You need this thing, grass area. Now it is up to you which type of section you choose. You can choose a rectangular section. You can choose this circular section. You can choose this a hollow section. You can choose this section. Or you can choose angle. It's up to you. It's about the availability of the sections. It is your choice. But as from the academic point of view, there is one section. Okay, mostly this section is used as a compression member. Okay, this section is also being used as beam member or flexure member as well. Okay, so it is your choice. But due to the limitation of the time, we will only do one example with one section. And I showed you that in the chapter number 1, we have now you can select any section. You can calculate the gross area for any section using the manual. You can use angle, you can use channel, whatever you want to use, but you will check the stability criteria. Stability criteria is this one for the tension member is this should be less than 300. And you have to check for the axial capacity, tensile capacity. You have to check your member for rupture. You have to check your member in the excessive deformation limit state. For the tension member. For the compression member, you have to use, again, you have to check that it is less than 200. Okay, you have to check the axial capacity in the compression. So we are just giving you the analogy. Now it is up to you. You spend a lot of time, you repeat all the questions with different sections. So in that way, you will develop the capacity. So there is a complex engineering problem in your course, and we will set you free to use any section. Okay, so I will discuss this CEP with Dr. Fahad, and most probably in the next class or so, we are going to assign it to you. आपके सवाल का जवाब मिला आपको क्या नहीं?
सर मेरे कहने का सर मतलब ये था कि सर हम जब ट्रस लेते हैं तो सर उसमें बहुत ज़्यादा कंप्रेशन मेंबर आ जाता है और बहुत ज़्यादा टेंशन मेंबर आ जाता है जो कि हम कैलकुलेट करते हैं स्ट्रक्चर एनालिसिस में तो सर तो इधर तो हम सिर्फ एक मेंबर की डिज़ाइनिंग करते हैं सिर्फ एक मेंबर लेते हैं ना सर उधर तो बहुत ज़्यादा मेंबर होते हैं बहुत ज़्यादा तो सर मेरे कहने का मतलब ये है कि हम डिज़ाइनिंग सब मेंबर्स के लिए करेंगे या सिर्फ इस तरह एक के लिए करेंगे?
सबके लिए करेंगे यार, सबके लिए करेंगे, अलग अलग।
ओके ओके सर, थैंक यू।
वो तो आप तक है ना, देखिए अभी मैंने बताया ना, अब हम आपको ट्रस्ट दे देंगे, आपको कहेंगे कि चलें, हम सबको पता है कि ट्रस्ट में आइदर यू हैव कंप्रेशनल मेंबर और यू हैव अ टेंसाइल मेंबर, ठीक है? तो यू आर फेमिलियर विद टेंशन मेंबर और कंप्रेसिव मेंबर कैसे करते हैं, यू कैन डू इट।
ओके सर।
You
Okay, sir.
are familiar how to do welded connection design. You are familiar how to do the bolted connection design. You can do slip critical connection design. We have developed we are trying to develop that capacity. Okay.
Yes, sir.
Any other question? Let me check how many of students are present in the class now. Oh, 20. Achha, let me check how many of you have submitted the quiz. Let me check. Where is quiz 1? Yes. Oh, good. आप लोगों का कोई सवाल है कि नहीं? मेरा तो गला खुश्क हो गया।
नो सर।
आप लोग सो रहे हैं?
नो सर, सवाल नहीं है सर। थैंक यू सर।
चलें, ओके, आप में से जो जाना चाहता है वो जा सकता है, और इंशाल्लाह अगर नेक्स्ट वीक में स्ट्राइक हुआ तो फिर